Hello, my name is Jared Coleman, and I will be presenting our work on graph convolutional network-based scheduler for distributed computing in the Internet of Robotic Things. So complex distributed applications are often modeled as task graphs where the output of one task is input to one or more other tasks, as you can see here in the figure. Task graphs are then scheduled to run on networks of compute nodes with varying communication and computation capabilities. Some tasks might be scheduled to run on one machine, while other tasks are scheduled to run on another machine. The overall goal here is to schedule tasks efficiently in order to minimize the make span or total execution time of the task graph. A few examples of distributed applications that are modeled as task graphs include crop cycle computations. That's the example that's in the figure here. Applications in genomics, like this example pictured here, which is executing various genome sequencing operations. In image processing, montage is a distributed application for creating mosaics from astronomical images. So this is another example of a complex application that's modeled as a task graph. Facial recognition is another example in the area of image processing and machine learning. Also, many IoT applications are modeled as task graphs. This example here shows a node-RED flow for an IoT application. And there are so many other complex applications that can be modeled as task graphs. This is a really common thing. On the other hand, autonomous robots are used in all kinds of applications. In airport security, in space and on other planets, on the battlefield, and on farms, just to name a few examples of where distributed mobile robotic systems are used in real-world applications. So the problem we're interested in involves scheduling and executing these complex task graphs on networks of mobile compute nodes. Traditional algorithms are insufficient because they don't scale to task graphs with many tasks, and they also don't scale for large networks. Most importantly, though, they can't produce schedules fast enough for systems of mobile compute nodes where the communication strengths are highly dynamic. So our proposed solution is to leverage our recent work in training graph convolutional neural networks to imitate traditional algorithms, producing similar schedules at speeds several orders of magnitude faster. And this table shows some of those results, comparing the GCN scheduler to a traditional scheduler, Heft. The GCN scheduler has been proposed to perform the scheduling task more quickly for any objective, make span, throughput. In our demonstration, we're concerned with make span, the total execution time of the task graph. Since the problem of scheduling has to do with graphs, task graphs, and a network, which is basically a weighted complete graph, a GCN can capture the underlying relations between the components of these graphs by generating embeddings based on the local neighborhood. The idea behind GCN Scheduler is to combine the information of the task graph and the network into a single graph, which can be fed into a GCN model, by carefully designing the node features and edge features. Since the task graph is directional, the GCN scheduler uses EDGNN, a GCN model for directional graphs, on this carefully designed new graph. This new graph has the same set of nodes and edges as the original task graph, but with additional features coming from the network settings. More specifically, node features for a task I represents the time required to compute task I over all machines, and the feature of the edge between task I and task J represents the required time to transfer the result of task A to task J across all pairwise machines. For our demonstration, we will show how the GCN scheduler, running on a laptop, can quickly schedule a task graph to run on a network of 4 mobile Turtlebots equipped with Raspberry Pi devices. As one of the Turtlebots moves out of range of the rest, its connection is lost, and we'll see the GCN scheduler quickly adapt to schedule tasks only on the available nodes in the network. In this scenario, a static schedule would have rendered the system completely incapable of executing the task graph, since one of the expected compute nodes was lost all of a sudden. Finally, when the Turtlebot returns and regains connectivity, we demonstrate how the GCN scheduler is quick to take advantage of this extra processing power and starts to schedule tasks on the returned node again. In this demonstration, we showed how GCN Scheduler, a model trained to learn the behavior of a heuristic scheduler, in this case Heft, can be used to quickly produce schedules for systems where network conditions change rapidly. In the future, we're looking into addressing issues with noisy bandwidth measurements, time synchronization, and network congestion issues. Also, we're trying to find new methods to deal with unpredictable results from when a learned model is faced with unforeseen edge cases.